This is another video just describing the thermodynamic processes of pressure volume graphs. We're going to look at this graph here, and let's say identify 3 points on the graph. Let's put a point right here, and let's call that point A. And then let's go over here and call this one point B. And one more point down here is point C. The first thing you should do always is get the temperatures at each of those locations using the ideal gas law, PV equals nRT. So let's go ahead and do that. Well, our pascals here is 4 times 10 to the 5th, and our volume is what, 10 times 10 to the minus 3. So let's go ahead and do that. So then I've got 4 times 10 to the 5th, and I'll multiply that by 10 times 10 to the minus 3 equals 1 times 8.31 times T. I'm using 1 for mole because it says use 1 mole, and it's a monatomic gas. And that turns out to be 481 Kelvin. Let's do likewise here. We have 4 times 10 to the 5th. And we'll multiply this by 20 times 10 to the minus 3 equals 1 times 8.31 times T. And that gives us 963 Kelvin. And lastly, at point C, we'll have 2 times 10 to the 5th multiplied by 20 times 10 to the minus 3 equals 1 times 8.31 times T, and we find out that C is 481 Kelvin. Okay, so let's look at the thermodynamic processes. Let's say we go from point A to point B, and our driving equation, I'll write it over here, delta U equals Q plus W. So internal energy change is a sum of heat flow and pressure volume work. It's also known as the first law of thermodynamics. So let's go from A to B. I'll put little dash lines here. If I want my pressure volume work, I can think of taking the area under this curve. Or since we're isobaric, you can just think of that as pressure external multiplied by change in volume. So let's go ahead. I'll label this one transition from A to B. So let's get our work. Work in this case is going to equal minus our pressure, which is 4 times 10 to the 5th. And that's going to be multiplied by a change in volume of, looks like 20 minus 10, so it'll be 10 times 10 to the minus 3. And that's going to equal minus 4,000 joules. That's negative because our gas is expanding against an external pressure. Therefore, it is work being done by the gas, so therefore negative. Okay, but we need to calculate delta U, so we need the Q value. So Q, and this is going to be a sub P, meaning the heat flow at constant pressure is going to equal number of moles N times the molar heat capacity for constant pressure times change in temperature. So what is that going to equal? Well, Q sub P is going to equal 1. Now, for a monatomic gas, C sub P is 3/2 times 8.31 plus 8.31. Okay, and I'll finish that parenthesis there. And then we need to multiply that by the change in temperature. Okay, well, it's 963 minus 481. Okay. And what does that end up equaling? Well, it's equal to 10,014 joules. I'll write that over here since I'm out of space. So 10,014 joules. And that's a positive because our temperature has increased. Okay, so then, but we want delta U when we're finished, so delta U will equal that 10,014 and then minus 4,000. And that'll give us 6,014 joules. So that's the total total energy change, okay, for the gas during that transition. Okay, so let's go back and do a new transition. So that was from A to B. Relabel this. We want to go from B to C now. So let's relabel this as A, and this is B, and this is C. It might be a good idea for us to write our temperatures here just to make sure we've got it. So this is 481 Kelvin. This is 963 Kelvin. And this is 481 Kelvin. All right, I'll change colors to make it clear. So we want to go from B to C now. Well, in this case, there's no pressure volume work done. So if you look at our equation, I'll write that over here again. Delta U equals Q plus W. If work is equal to 0, then our internal energy change just equals Q sub B. So delta U is going to equal Q, the heat flow at constant volume. Okay, so what is that going to equal? Well, delta U then will equal N C sub V delta T. And C sub V is the molar heat capacity at constant volume. So delta U is going to equal 1 times 3 halves R, because it's 3 halves R is C sub V, multiplied by the temperature change. Well, that's going to be 481 minus 963. Because we're going to have a lower temperature now than what we started. Okay, and that's going to equal minus 6,025 joules. So that's what delta U is equal to. And again, that's just a heat flow leaving the gas as it goes from B down to C. So the gas is decreasing, okay, in pressure, but the volume is staying the same. And it decreases in pressure because the temperature has gotten lower. All right, what about the last change? If we go from A directly to C. So I'm trying to draw that dashed line there. Well, we see that pressure and volume are both changing. So how do we handle that? Well, again, our equation is delta U equals Q plus W, right? So the first thing we need to do is recognize we can calculate the work done by looking at this trapezoid here. Work is always the area under the curve. And it's going to be negative again because our gas is expanding. It's going from 10 to 20 times 10 to the minus 3 meters cubed. So let's go ahead and get our work done using the trapezoid rule. Work is 1/2. The base one looks like 4 times 10 to the 5th. Plus base 2 is 2 times 10 to the 5th. Multiplied by our height of the trapezoid. Again, we're getting the area of this trapezoid. And that looks like it is 10 times 10 to the minus 3. Okay, and it looks to me like that's negative 3,000 joules. So I had to add the negative to that. When you do the area under the curve, the negative does not automatically appear there. So you have to remind yourself that since the gas is expanding, you've got to put the negative there. Okay, so then how do we get the Q for this? Well, the key is looking at delta U. Delta U is always equal to N C sub V delta T. Okay, delta U is always dependent on the temperature change. Always, 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 always. So we can always calculate delta U regardless of what's happening. So in this case, delta U is equal to 1 times 3 halves times 8.31 multiplied by the temperature change of 481 minus 481. So we see that delta U is actually equal to 0 in this particular case. So regardless of what's changing in here, delta U is always this equation because delta U depends on temperature change. Okay, so in this case, we can easily know that Q has to equal a positive 3,000 joules in order for us to end at the same temperature at which it started. So the heat flow has got to equal the amount of pressure volume work that's being done, except opposite in sign. Okay, so what's happening in this particular interchange here is as the gas is expanding, heat is being absorbed. Okay, and at the end, the total amount of heat absorbed equals the total amount of work done by the gas. And that's how we handle thermodynamic processes.